So in this next question, this is the start of group 2 chemistry. So they tell you the white suspension of MgOH2 because the solubility of the group 2 hydroxide increases down group 2. Oh, guess what? This is the fixed essay that we'll come to in a little bit. What is this reaction? Mg3N2 plus water. You get MgOH twice plus alkaline gas. Alkaline gas most likely is NH3. I need to balance this equation. There's 3 magnesium. I need 3 magnesium there. There's 2 nitrogen. I need 2 nitrogen there. There is 6 oxygen. O2 times 3, there's 6 oxygen. I need 6 there. I have 12 hydrogen. So 3 times 2 hydrogen is 6. 3 times 2 hydrogen is 6. 6 plus 6 is 12. The hydrogen are balanced out. So that's fine. So you have an excess of water. So that's not what you want. You want that. So the MR of Mg3N2 from your periodic table, 24.1 times 3 plus 14.0 times 2, I got 100.3. And I do that because we are going to do some mole calculation. So from your relationship above, you can hopefully see that 3 mole of magnesium hydroxide is obtained from 1 mole of magnesium nitrite. If you've seen my other videos on mole calculation, you can catch on A-level concepts under mole concept and stoichiometry. This is how I always do my calculation. Mole ratio from balance equation, and then the actual amount that actually reacts in the reaction. So on the right, the top bit is magnesium hydroxide. That is the mass I want. What is the MR of magnesium hydroxide that I want? Because mass over MR will give me the mole. It's 24.1 plus 2 times bracket 16.0 plus 1.0. I get 58.1. So there is my mole of magnesium hydroxide that is actually obtained. That's the mass I want divided by MR. That will give me the mole of magnesium hydroxide actually obtained. And then at the bottom bit is the mole of magnesium nitrite that is actually reacted. So the mass over 58.1 is 3 times 2.52 over 100.3. I can move up the 58.1. Okay, I was just showing you in one more step. And then I could get that relationship there. And I got 4.379. This data were given to 3 significant figure, 1, 2, 3. I show the calculation that will have a lot of decimal place to a bit greater before I run it up to 3 significant figure. So do not run up straight away. Always show it to a more number of significant figure because it allows you to check your responses. Okay, next question. When you hit the isocyanates, they hydrolyze the amides, well, the amine salt, okay? Because this is acid, the amine salt is basic. Well, amine is basic, and therefore acid and base, acid hydrolysis, you always get the salt. I'm sure you know it from AS chemistry. Under ester hydrolysis, when you do base hydrolysis of ester, you don't get the carboxylic acid, you get the salt. Always very commonly asked in MCQ, but you cannot say that they cannot ask you in theory paper, right? So make sure you know you're in acid hydrolysis or base hydrolysis. This is the kind of mole calculations dealing with stoichiometry, which would have come out in AS, if not in A2, I guess. Here you get to do a bit of calculations. So the mole of the barium carbonate produced is a solid, so I can use mass over MR, which is 1.66. If I work out on the side, the MR of barium carbonate, go straight to the periodic table. A good old friend, barium plus 1 carbon plus 16 times 3 is 197.3. And that will give me 8.4136 times 10 to the minus 3. I look at the value given. There are 3 significant figures, so I can round them up. 8.41 times 10 to the minus 3 mole, 3 sig fig, okay? Appropriate number of significant figure, yeah? write my handwriting a bit better there. Hence, calculate the MR of the original isocyanate. Why are this kind of question really difficult? Yeah. What do we know? What do we know? The R and CO give you CO2. The R and CO give you CO2, 1:1. The CO2, which is acidic, it can react with base. Okay, so the base can react with acid to give you the salt and the water. Okay, so the base, so the CO2 here is 1, and the barium hydroxide there is it barium hydroxide we're worried about? No, we are going to use barium carbonate because we have worked out barium carbonate here, right? So CO2 is to barium carbonate. From reaction 1, which is this, 1 mole of R and CO give you 1 mole of CO2. From reaction 2, which is this, 1 mole of CO2 give you 1 mole of barium carbonate. Because this is the same, 1 and 1, so when you do the LCM of 1 and 1, it's also 1, so you can just bring them down. You bring that down is 1, you bring that down is 1. The reason of comparing mole ratio before you start doing calculation, as you see, is only 1 mark. It's that you can see is R and CO and barium carbonate that you want. Okay, so those are the only thing that you want. So the mole of the R and CO over the mole of barium carbonate is just 1:1. The mole of the R and CO, the R and CO is given as a mass, so 1 gram there. So 1 gram divided by the MR. That is what you want, right? Mass over the MR give you the mole of the R and CO. Okay, you know it's 1 gram because it's stated in the question. And the bottom bit is your answer to the previous part. If I were you, I probably wouldn't use 8.41. I'll probably use 8.4136 because that wasn't very accurate. Anyway, if you rearrange the equation, then you will get, I hope you can see that you will get 8.4136 times 10 to the minus 3. Rearrange this equation. It's like 1 over A over B is 1 over A divided by B. It's like 1 over A times 1 over B. Okay, it's like 1 over AB. So 1 over 1 equal to 1 over this time MR. I just move the MR upstairs and then I let that remain at the bottom there. If you can't see this properly, I guess, you know, just do it the long way, and hopefully you can see it. Okay, 119, 3 significant figure. Okay. Now this next bit was actually where I made a mistake in my previous lecture tutorial, so I had to re-edit the video a little bit to show the correct calculations rather than my mistake in the calculation previously. So let's read the question carefully. So we have 1590 tons of SO2. We're working in tons here, which is why our final answer here is in tons. These are to do with reacting masses. So reacting masses are year 9 chemistry topic, and you should be able to, you know, get to the stoichiometric ratio based on a lot of my tutorial videos on stoichiometric and mole calculations kind of thing. So we get this. We want the tons of H2SO4, which is this, and this is coming from SO2. So here there are 2 equations. There's a shortcut to this. The shortcut is basically using ratio. The SO2 give you SO3. The SO3 give you H2SO4. These are a series of equations showing you the oxidation of SO2 to SO3 in the atmosphere, in the upper atmosphere, without a catalyst. Instead, you're using NO2 as a catalyst there without another external catalyst. And of course, once you get to the SO3, then you just dissolve in rainwater to give you acid rains. Looking at the first equation, so we have 1 SO2, 1 mole of it give you 1 mole of SO3, and it is this 1 mole of SO3 that actually get converted into 1 mole of H2SO4. So when these are 1 and 1, this means they have a common ratio. Otherwise, if they are not 1 and 1, we have to, you know, get them to be balanced by multiplying each whatever row to get to the lowest common multiple. So in doing this, So when they're the same in doing this, I have just gotten 1 mole of SO2 reacting with 1 mole of H2SO4. So I could get the mole of SO2 is exactly equal to the mole of H2SO4, because 1 mole of these will give you 1 mole of that. Therefore, it's just equal to 1/1. Therefore, they are equal in that regards there. So in terms of masses, I need the mass of H2SO4 and I need the MR. So if you go to your periodic table, you would have 2 times 1.0 plus 32.1 plus 16.0 times 4, you get 98.1. So mass of MR, that give you the mole, but this is in tons. Therefore, the mass of SO2 here was 1590 tons, so that was in tons, and this is divided by the MR of SO2, which was 32.1 plus 16.0 times 2, I get 64.1. So what you do then really is you just do cross multiply correctly, and you will get the mass of H2SO4 as 1590 over 64.1 times 98.1. That will give you 2433, and this has to be in tons. Okay, so 2433 there. What's next? So to give you a stage 3, they can react with ammonia to give you ammonium nitrate. You want the volume of nitrogen dioxide to make 40 tons of ammonium nitrate. Do you see this is equation 1 and this is equation 2? There are 2 different equations, yeah? We are working with tons, alright? So you need to be careful, because in mole calculation, mole equal to mass over MR, that is in gram, that is in gram per mole. Okay, so you need to be careful of this being in gram, and we are working with tons, and they want the volume, and they don't say the units there, so you need to be very careful, because we also talk about the molar volume of a gas being equal to 24 dm cube per mole. 1 mole of any gas occupies 24 dm cube per mole, but we can also think about 24,000 cm cube per mole. So these 2 quantities are equal, so it really depends on what you're using, and that will justify whatever units you have at the end there. They don't provide you a unit, which means that if you don't write a unit, you are done. You already lost a few marks, okay? There's physical chemistry for you, okay? Let's compare mole ratio. What do we know? We want nitrogen dioxide, and then we have that. So we know we want 40 tons of it. This comes from this, and this comes from this. So to relate this and this, we need to go via the HNO3. That is our relationship, okay? I'll show you a shortcut, and it is to do with ratio. I don't know if you understand it, but try to bear with me, okay? What does equation 1 show you? Actually, let me show it first. NO2 is to HNO3 is to NH4 NO3. We are given that information, we want that information, okay? But somehow we have to go through the middle point, because this is not formed directly from this, right? This forms this first, only then this forms this. Because this is not here, only this is here. So this is our connecting link between the 2 equations. For the first equation, shows you that 3NO2 forms 2 mole of HNO3. 3 mole of it forms 2 mole of it, okay? The second equation shows 1 mole of it form 1 mole of it. 1 mole of this form 1 mole of this. But notice that these are not the same. Because they are not the same, this ratio are not exactly 3:1, because they are not the same. How can I make them the same? Only when these 2 are the same, because they represent the same substance, only then I can compare them directly. So I have 2 different equations now, right? So the LCM of 2 and 1 is just 2. So 2 times 1, because 2 times 1 is 2. How do I get from 1 to 2? 1 times 2. So I times by 2 throughout. So what would I get? I would just get 2 is to 2, which is the same as 1 is to 1. Still the same, right? What do you get overall then? overall, now you can compare 2 because now they are equal. Now they're equal, I can just bring them down, and that means it's 2. So it's not 3:1 ratio, it's 3:2. That is our important bit because this is what we have, this is what we want. That is the shortcut that I was going to show you. That means you don't have to work out anything about HNO3. You can just link them straight together because you already work out the relationship just by using LCM, your primary school lowest common multiple. Alright? So the mole of NO2 divided by the mole of NH4NO3 is 3/2. 3 mole of this will form 2 mole of this based on this reacting mole ratio. Okay? You have seen me using these fractions in the other video as well, yeah? When I do O-level or A-level papers, I love this method, okay? It's up to you if you don't like it, alright? You can always use your own method, really depends. I'm going to use 24 dm cube per mole, so I don't write down the unit, but in my mind, I'm really thinking it's dm cube per mole, so this is the volume of NO2 in dm cube. So let V equal to the volume of NO2 in dm cube. That's why I'm using 24, okay? So the top bit is the mole. This is actual. This is from the reacting mole ratio from balance equation. This is actual mole. The actual mole of this is 40 tons. So it's 40 times 10 to the 3. That is 4 kilogram. And then I need to multiply by another 10 to the 3 to convert kilogram to gram, okay? What is the MR? The MR of NH4NO3, get it from your periodic table. So 14.0 plus 4 times 1.0 plus 14.0 times 1 plus 16.0 times 3. I'll get 80.0. Of course, your calculator will not show you 80.0. Your calculator show you 80. But I choose 0.0 because, you know, your periodic table shows you to 1 decimal place, right? So there's your accuracy there, which you are lost if you don't include them in, okay? So you should be very careful with your arrangement of formula here. So the volume of NO2 is going to be 3/2 times, should probably make some more space for myself, 40 times 10 to the 6, because I simply can simplify 10 to the 3 times 10 to the 3, that's 10 to the 6. Or you can say 1 ton is 10 to the 6 gram. And then I move up to 24 again. And you know what? I know where I gone wrong, okay? Have a look at this. You see this is 80.0. So I literally wrote down 80.0, but it looks very, very close, like 800 there. So it turns out that it's very easy to make mistake. So with any calculation, you gotta check your calculation twice, okay? Especially when doing, and also because you cannot be sure that you will have time to check your answer ever again, right? So you gotta check it as you go along. So that's 1.8 times 10 to the 7 dm cube. So that's 1.8. Do I want 2 sig fig or 3 sig fig? I mean, there's technically 3 sig fig, but the data was given to me 2 sig fig. Maybe I can just do 2 sig fig. I'm sure it'll be alright. Okay. So if I had used 800 instead of taking note of this 80.0, which I have written very carelessly just now, I might have gotten the wrong answer. Okay.